Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the next talk is from the University of Cambridge.
Is this on? Yeah. Okay. All right. So I'm going to talk about statistical machine learning for search. The title was going to be for user modeling, but there are obviously difficulties doing that with this particular data set, which I'll get to at the end. And this is part of a kind of larger interest that we've had in the interface between machine learning and search over the last couple of years, even a little bit before we got this data. So this is joint work with Frederick, who's sitting right there, and Catherine Heller, who started out originally in this area. Okay, so let me start off by asking the following question. What do Jesus and Darwin have in common? Okay. Any ideas? Yeah, they're both on this slide. Yeah, beard. Beard seems to be the canonical answer whenever I ask this. Anyway, so Google has this tool in its lab section called Google Sets. And so you can type in Jesus and Darwin, and it says, enter a few items from a set of things, next press large set or small set, and we'll give you other items from this set. So you can type in Jesus and Darwin, and here's what Google thinks. Darwin, Jesus, Churchill, Gonville, Keyes, Downing, Girton, Lucy Cavendish, Fitzwilliam. Now, half of you are probably, 95% of you are wondering what the hell this list is. It turns out this is a list of the names of colleges at Cambridge. So Jesus and Darwin happen to be names of colleges at Cambridge. And so one way to complete this set of items is to say, aha, these are colleges at Cambridge. This is the rest of the list. So this is kind of a fun tool. You could play with it. It doesn't actually work that well, Google Sets. But it really inspired us to think about, it really inspired me and Catherine originally to think about search in a machine learning context as finding sets of items. So the problem that we were interested in was clustering on demand. So imagine you have some universe of items. They could be web documents. They could be other kinds of documents, images, proteins, whatever. You have some universe of items. So here we have a yellow train, a blue car, a yellow car, a London bus, etc. And what we want is we want a query in this sort of generalized context to be some subset of that set of items. So here we have a red car and blue car. And if we give a red car and blue car, we would expect to get back cars. But if we give a red car and a tomato, we would expect to get back tomatoes. So it's a bit like doing clustering on the objects, but we're seeding the clustering with the items in our query set. So we're calling this clustering on demand. And it's actually a problem that we can think of as generalization from a small set of items. So imagine that your query is a set of items like these blue dots. And we should be able to rank other items X by how well they fit in with the query set. Okay, so here this X doesn't fit in very well with this query set of items in some feature space. Here this X fits in much better somehow. And there's actually been a lot of work in cognitive science on how humans generalize from a small set of items. We do this all the time. We observe a few items from some category, and we can generalize incredibly well to other items. And I was very inspired by this. I have kind of a background in cognitive science, and so I look into this quite a bit. And this literature goes back to Tversky and other great names like Roger Shepard. But most recently, Tenenbaum and Griffiths, two people I have a huge amount of respect for in cognitive science, have come up with a really nice Bayesian model for how humans do generalization from small sets of items. So we're now thinking of the interface between machine learning information retrieval, and this sort of Bayesian cognitive science. Okay, so the approach that we have for finding sets of items is the following. We want to rank each item in our universe of items by how well it would fit in to a set which includes our query items. Okay, so D sub C is going to be our query items. The C stands for a cluster. It's a subset of the big universe D. So our query is some set of items, and the ranking we want is basically the items in our universe ranked from best to worst somehow, by how well they fit in. And what we're going to use is a Bayesian, that is a model-based probabilistic relevance criterion that's based on these human models of generalization. We obviously, for search problems, we want to limit the output to the top few items, not the whole universe sorted. So, so just a little background on how we do this Bayesian inference, and then I'll talk, the second half of this, I'll be specifically talking about the query logs and how we can think of the query logs and try to do interesting things from this perspective. So here's what we have in the most general setting. We have some items X, whatever they are. They have some feature representation. And we define a family of probabilistic models for those items. So that's just probability distributions over X parameterized by some parameters theta. So for example, if X is real valued, you could have Gaussian distributions. Theta would be the mean and variance of your Gaussian. Okay? Now, to do Bayesian inference, we need to define distribution over thetas. Otherwise, our model is not fully specified. We've said there's P of X given theta, but we haven't told you what the distribution over theta is. So we have to have a prior over our model parameters, P of theta given M. Now, imagine you observe a data set D of n items, and you have some model class M, like the model class of Gaussians, let's say. Now, for that data set, we can compute the probability of observing that data set under our model assumptions. And that probability is the probability of observing the data set for any particular setting of the parameters of our model. But because we haven't observed the parameters of our model, we have to integrate over all possible parameters. That's where the prior comes in, weighted by the prior. This integral here, just by the basic rules of probability, gives us the probability of observing any particular data set under our general model class. Okay? This is called the marginal likelihood or integrated likelihood or model evidence. It has lots of different names. And in a setting where we assume that our data points were drawn independently from our model, so IID draws from our model, then the probability of the data for any particular parameter is a product over the data points of the probability of each data point given the parameters of the model. Okay, so here's how we're going to use this to do retrieval. So having observed a set of items DC in our query is going to be a set of items from our universe of items, and we assume that they belong to some concept. Now what we want to know is how probable is it that some other item X in our universe of items also belongs to that concept. Now what we really want to know is the probability of observing X, given that we've observed the items in the query set, that's P of X given D, relative to the prior probability of observing X. Just because in our universe, some items are going to be more typical than other items. We want to normalize out for that. We want to really just consider how much does our query increase or decrease the probability of observing X. This is a very simple scoring method for items in the set. To actually compute this in any particular setting, we need to assume some simple parameterized model, P of X given theta, and prior over the parameters, P of theta. And since the parameters are unknown, to compute all these scores, we need to average or integrate over all possible settings of the parameters, which is what I showed on the previous slide. Okay, so there's actually a really interesting way of seeing this score, we can just take the score that I've written in that red box and rewrite it as the thing at the top here. And when you do that, it has a very nice intuitive interpretation in terms of hypothesis test, a hypothesis comparison. So we can represent that by graphical models if you're familiar with graphical models. But this is a really nice way of capturing the intuition. So here's what we're doing. Our score is a ratio of two probabilities. On the top, what we have is the probability that the item we're scoring was generated from the same model with the same parameters as all of the items in our query set. And on the bottom, what we have is the probability that the item we're scoring was generated from some parameters, theta, that are not the same as the parameters theta prime that generated the query set. Okay? So this captures the idea that an item belongs to some particular set of items by saying that to belong to that set of items, it means that you were caused essentially by the same theta. Yep?
You're going to be very optimistic about how you're generating x here, because you're going to tune theta perfectly to x, right?
No, we're not doing any tuning. That's the main difference between Bayesian inference and machine learning methods based on optimization. We don't optimize theta to fit the training data. We're integrating over all possible thetas.
Sure.
So there's no problem with overfitting.
But what about multiple x's that you might want to explain apart from x1 through xn? You're looking at one x at a time here, right?
So we're scoring each item at a time independently by how well it fits in with the data set. But let me just move on, and maybe we can take that question later. Okay. So this is the scoring criterion. The algorithm is the following. Your background is you have a set of items D. You have some probabilistic model. You have a prior on the model parameters. And then your input is some subset of the universe of items. So that's D sub C. And then for every item in the universe of items, you compute the score. And then you return the elements of the universe sorted by decreasing score. So it's not really an algorithm. It's a very trivial algorithm. So for very simple models, for example, in the exponential family, computing the exact score is tractable. So you might have worried that you had all these integrals you needed to compute. But it turns out that for a large class of probabilistic models, we can compute the exact score very easily as functions of statistics we can compute from the data. Even for very simple models and almost no parameter tuning, there really aren't any. I mean, there are parameters in the prior, but other than that, there's nothing that we need to really think about here. We can get competitive results. We've done lots of different things. I can sort of talk about that if there's any time, which I doubt there will be. And then, but importantly, let's think about data that's represented in terms of sparse binary vectors. Okay, so it turns out that for sparse binary vectors, computing all the scores can be reduced to a single sparse matrix vector multiplication. So all those integrals, all that nasty stuff goes away, and it's a very simple computation to do. So what do I mean by that? We're assuming that our items x are big, long binary vectors of zeros and ones, and they're sparse, so there are very few ones. And if we use a multivariate Bernoulli distribution as our probabilistic model, so this is all of the, you'll see all of the details here now, then that's an exponential family distribution. We can come up with a prior for the parameters of that, which is called the conjugate beta distribution, which has this form, but don't worry about it. The point of that is that the Bernoulli distribution and the beta distribution are very natural buddies. They work very well together. You can multiply a Bernoulli by a beta, and what you get is another beta. You can compute all the integrals analytically. And then what that means is we can compute the score for a particular item. And it's this nasty expression involving a bunch of these things called gamma functions. These are generalizations of the factorial. The good news is, though, that you look at that expression for a while, and you simplify, and the nasty expression can be dramatically simplified. So if you want to compute just the log of the scores for all of the items, it turns out that ends up being a linear function of a vector that you compute from your query set. So you have a sparse matrix and a sparse vector, and you multiply the two. You add a constant that doesn't affect the rankings, and you get the scores of all of the data points. So you go through all this rigmarole, and then the great thing is you get a very, very simple algorithm. So, just for full disclosure, we developed this work while I was at UCL, and UCL wanted to protect the intellectual property, and a bunch of prototypes were built, and a company was started to kind of commercialize it and so on. But I was told by them that I'm coming to Microsoft, so I have to tell you guys this. So. Okay. So let's talk about query logs. So this is a great visualization of the query log data that Frederick produced. Here we have about 1% of the data. We have sessions by terms and sessions, and it's a bipartite graph. And it's just very pretty to look at.
What was sessions by terms and sessions? Not queries and sessions?
Sessions by our definition of term might be different. Let's think sessions by unique sort of query strings. Okay. All right. So we have data like this. What do we want to do with this? So here's something we might want to do. Given a set of query terms or set of queries, okay, imagine we represent each query by some big, long binary vector of features of that query. Now, can we use this idea to suggest other relevant query terms? Okay, so this is sort of like now an application of these ideas to query suggestion. Okay, you have a set of queries. You want to suggest other queries that somehow have similar feature representations. All right. So here's some statistics on the data. We can represent the data in a bunch of different ways. Let me just talk about the terminology. Imagine you have the data like this. So you have two sessions, session 1 and session 2. In each one, you have two queries. Britney Spears, Christina Aguilera is the first two. And let's say Britney Spears, Ticketmaster Britney Spears, or something like that. So in this data, we have two sessions. We have 4 queries. We're going to use the word term to refer to sort of unique strings in these queries. So we have 3 different terms, and we have 5 different words that are being used in here. So just to clarify the terminology. So what we're going to do is model it as a term by features matrix. So each of these terms, like Britney Spears, is going to be represented as a big, long, sparse binary vector of features. And so what are the features that we have? Well, the matrix that we end up getting here is a big, sparse binary matrix with 6 million distinct terms after we remove singletons and 5 million distinct features for each term. But it's very sparse. There are only 21 million non-zero elements in that matrix. And the kinds of features that we have are the following. For each term, like Britney Spears, we have the sessions that it appears in. We have the words, like Britney and Spears. We have the URLs of the results that are returned. And we have the URLs cut down to hosts, so removing a bunch of stuff at the end so we get just the hosts. Okay? So that's our big, long binary vector features. We're only using the data provided by Live Labs. Obviously, we could go out and try to use all sorts of other data, and it would be interesting to do that, but we haven't done that. So just a whole bunch of those numbers. Now you might worry that we're trying to do machine learning in a 5 million dimensional space. Now obviously if we were doing fitting of model parameters in a 5 million dimensional space, we would get a lot of overfitting. But actually, because we're doing integration over parameters, a lot of the uninformative features get automatically less weight under the algorithm. So rather than having kind of heuristic weighting techniques like TF-IDF and things like that, the algorithm kind of has a built-in automatic weighting of features by the relevance and so on. Okay, so how did we actually implement this? Frederick, throughout this year, has also been working on a lovely matrix library for Haskell, and he got this to actually scale very nicely. So querying takes on the order of 4 to 10 seconds on just a regular PC with this Haskell matrix library. Obviously, it could be implemented in any way you want. It's very simple computations. The sparse back end of this Haskell library was actually written in C++ to deal with sparse tensors and matrices, etc. Okay, so here are just some fun examples. If you query with 2 terms, so query is a set of queries. Okay, that might be a little confusing. Okay, so the query involves 2 individual terms, according to our terminology, Kyrgyzstan and Turkmenistan. If you use just the sessions part of the feature space, well, Kyrgyzstan only has 2 features in that it only appeared in 2 sessions out of all the possible sessions in the data set, and Turkmenistan in only 5 sessions. But there's enough information there, even when you have a total of 7 features out of 5 million, that the results are not completely ridiculous. So I mean, in fact, I don't actually know whether they're Miss America winners from these places, but I presume there's something related to that. Tajikistan, Azerbaijan, Afghanistan, Georgia, which is an ambiguous term, but fairly relevant to that, and China. So those are the top results. If you include more features, then you get a slightly different ranking. You get more, presumably more overlap, but you also get things that are slightly weird, like Nauru, capital of Pakistan. But they're still fairly reasonable, I would say. Obviously, what really needs to happen is this needs to be run on very, very large data sets or on richer feature sets. But even with on the order of 15 or 20 features per item, we can get amusing results. So here's another ranking with a slightly different set of features. We did a lot of comparisons of different kinds of features. We spent a lot of time implementing this on this particular data set. Here's some more examples. Celery, carrots, and cabbage, a set of 3 queries, and you get other interesting things, not all of which are related. So Cabbage Patch Kids Christmas, but I'll talk about that in a minute. This seems to be just related to cabbage, not to the other query terms. So we need to improve our scoring method to reduce that sort of thing. Cocaine and heroin, you get crack cocaine, crack energy drink, coca, etc. Black tar, heroin. I should have asked Frederick why he was doing this particular search. The interesting thing is, okay, here's another one, Gone with the Wind, The African Queen. You can get other movies out of there. It's still, I think the data set is a little too small to get all the benefits of this. And I also think that really what needs to happen is that we need to augment the Live Labs data with all sorts of other features that we can come up with. And I'm not afraid, we have 5 million features, I'm not afraid of having 100 million features because there's no fitting of model parameters here. So that's not going to cause problems. Amazon, Best Buy, now these have a lot of features, and you can see that items that have a lot of features tend to give you more reasonable results. So you get Circuit City, Electronics, Radio Shack, CompUSA, etc. And now, if you do search for Apple and Orange, you get annoying things like Apple Computer and Apple Macintosh. And so we can take our scoring method and now extend this Bayesian hypothesis testing to include negative terms. So we want to score things by how likely they are to belong to a set that includes Apple and Orange, but down-weighting by how probable they are to come from a set that includes Apple Computer. And if you do that, all the Apple stuff, Apple Computer stuff goes away, but then you get Orange County, and so you can downweight for that, and you get, again, more reasonable things, but obviously there are lots of uses of the term orange. Okay. So finally, one of the shortcomings is that some of the items, like if you search for blue and red, some of the items are only related to one of the query items. So the blue is related to blue, the red or color blue, they're each related to only one item. But if you again, modify the score to discount by relevance to single terms, then you can get, just from this data set, blue, red, green, orange, yellow, pink, black, and colors. Okay. So again, this is the discounting. You get a better list of drugs on this side than you do on this side. So, for example, energy drink goes away somehow. Okay. All right. So, okay. So, just in terms of implementation, I already mentioned the Haskell matrix library, and this is a nice way of showing that it scales very well. This is one of the things that Frederick has done. A very interesting contribution. This extends outside of this. Some future directions. We really want faster retrieval of the top-end items, and there are nice ways of doing approximate scoring by using bounds on these probabilities. One of the things that we're very keen to do is we are keen to take sessions and cluster them into sub-sessions, and we have a fast Bayesian algorithm to do that because people might be looking for certain things during a certain sub-session and then might switch to doing something different, and I think that would be interesting to do. And really, it would be quite fun to combine the data with all sorts of other data, social network data, collaborative data, and I'll mention that in a minute. So in terms of the quest for assets, the main limitation of the assets was unfortunately that the sessions are too short and there are no user labels. So we understand that's a privacy issue, but our original goal was to really do user modeling, and we weren't really able to do that. But we found interesting things to do with the data anyway. So it was actually very valuable. It was a really great thing to have. So that's the good, definitely. We're very, very grateful for the data. But the user modeling wasn't really possible. We also wanted to find trendsetters, which is even more sophisticated than user modeling. But that wasn't really possible with these short sessions. So research questions we'd like to address: user modeling, customization, and a combination of search, local context on somebody's desktop, and the social network data to improve search. Okay, so just to mention that the sort of general idea of looking for sets of items from larger sets of items is something that our group has been working on in lots of different applications. So I just wanted to mention that we have a lot of work on sort of image retrieval, looking for scientific literature, bioinformatics search, etc. So that's been a lot of fun. So great, thanks.
Thank you.
Yep.
Nico Erchak, NYU. I had several simple questions about your model. And
Sure.
the first question, where did you get priors for your
Okay, that's a very good question.
Bayesian learning is really sensitive to stress.
No, I don't agree that. I mean,
in your case, you had independent features, but if you drop this assumption, you might want to drop it.
Yeah. So there are two questions in there, really. Let me go back. Sorry. To maybe one of these pictures. Okay, this is a good one. All right. So we have 6 million terms by 5 million features. The way we get our prior is the following. So remember, the prior is the prior distribution on what concept you're going to search for. Okay, so we need to define this prior to somebody actually querying with a set of items. Okay, so what we do is we take the empirical data, the entire universe of items. We compute the frequency of each of the features in the items. Okay, this is some very small number between 0 and 1. And then we take a constant times that frequency. We always use the constant 2 in all of our applications. And that seemed to work fine. Now I've tried, we take that constant, c times the frequency. C times the frequency is the prior we use on the alpha parameters. C times 1 minus the frequency is the prior we use on the beta parameters. That constant c corresponds to a pseudo data set consisting of 2 items drawn from the average distribution of items in the data set. So it's kind of like a smoothing, a Laplace smoothing type thing. And the ranking actually is not all that sensitive to the prior that you use. So you can take that constant and you can increase it by a factor of 10 or decrease it by a factor of 10, and that almost never changes the actual ranking that you get. Obviously, if you increase it or decrease it much more dramatically, then you can have effects on that. So that's where we get the prior from. The main other thing that you mentioned the fact that we assume the features are independent. And we don't really believe the features are independent. So that's really an assumption of convenience. If we assume the features are independent, we can do everything using this sparse matrix vector multiplication. We can do blindingly fast retrieval. If we want a more realistic model of the distribution of features, then we trade off that realism for a slower retrieval. But in theory, I mean, the method can be applied to any sort of, if you're just searching on small data sets, you can have a very complicated probabilistic model and try to do these approximate integrals to do the search.
But then if you drop independence, then you actually have a larger set of features to use for each query, because currently you just use a small subset of features.
No, we use all of the features.
Yeah, but those that are not related to the query terms are actually kind of ignored in the ranking because they give constants.
So the features that don't appear in the query set will contribute to the constant. That's right.
They're not important. You just mentioned that number of features is not important for Bayesian learning, and I kind of disagree here because you don't have overfitting, but you may have simply noise. Because if you have just several parameters and a lot of features to estimate, then what you get basically is your prior. And you compare your elements based on
so anyway, it's a bit technical, but what we found in all sorts of other data sets as well, and I have a very simple understanding of it, is that the more features you add, I mean, obviously if you add complete noise in a malicious way, you will not improve the method. But the more features you add, as long as they're somewhat relevant, it doesn't hurt. Okay, if there's an extra information, it doesn't really hurt. And I mean, I can explain that offline if you want. Yeah?
How do you evaluate the effectiveness of your technique? So, for example, you have 2 results that you showed on the cocaine, one better than the other. So what's the metric that you're using?
Yeah, that's a really good question. We didn't do that at all in this setting. We have done more careful evaluations when we thought about things like image retrieval by looking at actual labeled data and precision recall curves in trying to predict the labeled data. And so this is not published work, the application to the MSN log data, and I wouldn't even dare to publish it or try to send it anywhere because we haven't done, as you say, we haven't done empirical comparisons. But yeah, it's needed. Yeah.
So you designed the distribution over the features, but is there a possibility of learning it along with
So it's actually learned in the sense that what I designed is a family of distributions. I said I want to model sparse binary data, and the distribution is actually learned. You can think of when you type in a query or a set of items, a set of terms, then what the model does is it learns the theta parameters. It learns the distribution over the theta parameters, and it tries to predict new data points. That's what it uses to score.
So you're saying you're doing some kind of soft feature?
It does some soft feature selection automatically. But if you wanted to compare, say, a multivariate Bernoulli with independent features versus one with some sort of dependency, there are ways of doing Bayesian model comparison. You can actually do that. But it's just more costly. We needed to do something fast. Okay. Sorry. I think we're done.
Yes, we're going to break. Thank you very much.
Okay.
And we start back.